Hey everyone, welcome back to our series on statistics. This is episode number 6, and we'll be visiting the sibling of the normal distribution, the binomial distribution. In a world of complex and abundant data, we are often only interested in binary options. This just makes life and decisions so much simpler. So more often than not, we are only interested in whether our favorite team wins or loses, and businesses are usually focused on whether they will be profitable or not. Hence, a random variable that stores these types of binary information is what we'll be learning today, the binomial distribution. So in this episode, we'll tour through 3 major topics. 1, the Bernoulli distribution. 2, the binomial distribution, where we will also revise binomial probability. And finally, we'll conclude with the classic question. A Bernoulli trial is a random experiment that only has 2 outcomes. It was named after Jacob Bernoulli, a Swiss mathematician who pioneered in combinatorics and probability. In his book Ars Conjectandi, he studied how much you would expect to win in various games of chance, which were later called Bernoulli trials. Fun fact, just casually, Bernoulli was the guy who discovered the constant E. No biggie. So a Bernoulli trial only has 2 outcomes, often referred to as success or failure. For example, the question, do you like your mum or dad, is Bernoulli because there are 2 possible outcomes. However, the question, who did you vote for in the last election, is not a Bernoulli random variable as there are more than 2 possible outcomes. So a Bernoulli random variable, say x, records the outcome of a Bernoulli trial. Since there are only 2 outcomes, by convention we let x equals 1 represent success and x equals 0 represent failure. As with all random variables we ventured through, we are also interested in its probability distribution. So we denote the probability of success, x equals 1, as p, and the probability of failure, x equals 0, as q. And since there are only 2 possible outcomes, q is just equal to 1 minus p. Because there is only 1 trial, the parameter of a Bernoulli distribution would be the probability of success p. Hence, we can specify the Bernoulli random variable as this. Once we know p, we can completely specify the probability mass function of a Bernoulli random variable. We just have a piecemeal function specifying the probability of each outcome. The PMF of a Bernoulli distribution looks like a histogram because it's discrete. Now, recall the definition of a mean. We can calculate the expected value of x, which is the sum of the products of each outcome and its probabilities. There are 2 outcomes, success equals 1 and failure x equals 0, with probabilities p and 1 minus p respectively. So the mean of a Bernoulli distribution is just p. Similarly, recall the 2 definitions of variance. It's just the expected value of the squared deviations. But we also learned a simpler way, which is the expectation of x squared minus the expectation of x all squared. Thus, we calculate e of x squared first. Then, because we already know e of x is p, the variance of a Bernoulli distribution is p times 1 minus p. Now, what if we run many Bernoulli trials back to back? This is what we call a binomial experiment. So there are 4 conditions to satisfy a binomial experiment. Number 1, the experiment consists of n identical trials. 2, each trial has only 2 outcomes, success and failure. 3, the probability of success p is a constant between all trials. And 4, the trials are independent. That is, the outcome of any trial does not affect the outcome of any other trial. So a binomial random variable, let's say y this time, is the outcome of multiple Bernoulli trials. So if there are n Bernoulli trials and x equals 1 represents success for each trial, y then represents the total number of successes in n total trials. Hence, y can range from 0 successes to n successes out of n trials. So in contrast to a Bernoulli random variable, for a binomial random variable, we need to know how many trials there were, n, and the probability of success of each trial, p. So we can say y is binomially distributed with parameters n and p. For a PMF of a binomial distribution, p of y represents exactly y number of successes in n trials. We will cover binomial probability in more detail in the probability series, but here's a quick 30-second recap. The probability of obtaining y successes is p multiplied by p y number of times. But because there are total n trials, if there are y successes, then there must be n minus 1 failures. So we must also choose the number of different ways our successes can occur from n trials. Hence, the PMF of a binomial distribution is this, and you can remember it in 3 easy steps. 1. Choose where the successes are. 2. Multiply by the probability of y successes. And 3. Multiply by the probability of n-1 failures. Now, to derive the mean and variance of the binomial distribution, it is much easier to start from our simpler Bernoulli random variables. Our binomially distributed y is just the sum of the n individual Bernoulli random variables xi. Like random variables, expectations are also linear, so we can split individual expectations. And since the mean of each Bernoulli variable is p, then the mean of a binomial becomes np. For variance, we can only split into individual variance only if each component is independent of each other. And since the Bernoulli trial xi are all independent, we can split the variance. And since the variance of each Bernoulli variable is p, 1 minus p, then the variance of a binomial becomes npq. So this is all great and all, but what does the binomial distribution look like? The PMF of a binomial distribution is again a histogram that has a peak around the mean. But depending on the value of the 2 parameters, we will get different shapes and sizes, which we will look further into in the next episode. So let's end with a classic question. We are in Edison's light bulb factory, and it is known that 10% of the light bulbs produced are defective. So Edison asks us to test a selection of 10 light bulbs to see how many are defective. A. Is this a binomial experiment? We need to ensure that the 4 conditions of a binomial experiment are met. 1. There are 10 identical trials. Tick. 2. Each trial has 2 outcomes, defective and solid. Tick. 3. The probability of defect, which we consider as success, is constant at 10%. Tick. Finally, the trials are independent, assuming that the factory produces many light bulbs, so the probability does not change over time. Thus, yes, this is a binomial experiment. B. Specify the Bernoulli and binomial distributions. Because each trial of a light bulb has a probability of defect 10%, we specify the Bernoulli distribution as this. Because there are 10 Bernoulli trials in the binomial experiment, we can specify the binomial distribution as this. C. What is the mean and the variance of this binomial experiment? This one's an easy one because the mean and variance of a binomial distribution is NP and NPQ. So substituting n equals 10 and p equals 10%, we just get a mean of 1 and a variance of 0.9. D. What is the probability of exactly 2 light bulbs being defective? Please try to revise binomial probability because it will be so much easier to answer these types of questions. So we want exactly 2 light bulbs defective out of the 10 trials. 1. We must find all the combinations where the 2 defect light bulbs can be. 2. Then we multiply by the probability of 2 defects. And 3. We multiply by the probability of 8 non-defects. So the probability of 2 defects out of 10 light bulbs is 19.4%. So that's it for episode number 6. We toured through the Bernoulli distribution and binomial distribution. So tune in to our final episode on the most misunderstood theorem in maths, the central limit theorem, and we'll also learn the link between the normal and binomial distribution through a technique called normal approximation. Or click here to watch episode 0 on the big picture of statistics. So like, subscribe, and leave a comment below on what you would like to learn in the future. I'll be there.